Dear students, today's topic is the logic gates, and it is the topic code is ELEC-DIGIE-S3B, Digital Electronics, section 3B. We have done in the section 3A the conceptual understanding of the logic gates in terms of the statements, how the logic gate is explained or defined. Now we will be taking in this topic the technical side of the logic gates, and all various basic logic gates we will be discussing, and the various other derived gates which are used in the digital electronics. Those gates will also be discussed. So first logical operation, we as already discussed that the logic OR operation, or this is called logic OR function or logic OR gate. The logic OR function output is only true if the one or more of its inputs are true, otherwise the output is false. We have already defined that the output is 1 if any one of its input, this is the logic OR gate, if any one of its input is 1, have the state of value 1, then the output, in this case let's say Q is the output, A or B, then if any one of its input is 1, the output is 1. Otherwise, if all of its input are 0, then the output is 0. In case the false means, otherwise means, in this case means that if input is 1 but if you are getting 0, that is output is false in that case. Now we take the equivalent, in order to understand this logic OR gate operation, this is called the discrete circuit or the electrical circuit which explains this logical operation. Remember this, we will see that the on off state, this is a variable, binary variable. This is just like a switch is in the state of either on or off, right? So in digital electronics we use the switching process. The gate job is to switch on and switch off, turn on the switch and turn off the switch. On and off of the switching process is taking place. So let's first go through that the typical conventional circuits. There is a lamp, there is a bulb. When it is turned on, so it means that it is equal to 1. When it turned off, it is equal to 0. So there is a circuit, series circuit, but in between there is a two parallel, one parallel circuit of two branches, each labeled as A and B switch. Let's say this is A input and B input. Now if suppose this is a battery, the current, we will be now considering the state of this output is Q, which is the outcome of the two inputs. So let's say if A is 1, let's say, or start with the A is 0, B is 0, means both are off state. So what will happen, this circuit is open circuit, current will not be flowing in this circuit, current will reach only here. Let me show, current will reach up to this position, this level. Okay, so that means that the output will be, the bulb will be off. So that means that is true statement, that if input is A is 0, B is 0, output is 0. So lamp is off, off means Q is equal to 0. So that is true. So it is showing that the for open switch means the off switch in 0 and close means the on switch means it is equal to 1 for both A and B where binary these inputs. Now if A is 1 and B is 0, so what will happen, the current will pass through, this is now is the on state, A is 1 means we will turn that the switch on, the current will pass through this path A and it will reach to this bulb and bulb will turn on. So if even B is 0, B is off, this is A is 1, B is 0. That means output is equal to 1. So turn it on. And similarly, if any one of the or all of these inputs switches both are on, or any one of them is on, the bulb will be on. So that is the logic OR gate operation which is performed. Now let us see how the electronics inside the electronically we do that. So here we have, you can see that what we utilize the transistor. We can make this switch, that is the OR gate switch, from the diode as well, from the transistor. The transistor TTL we call transistor logic circuit. As I already told you that at the back what we have got all these analog electronics at the back of the digital electronics. It is made from the packed component of the diode and the transistors, various components connected in such way they perform the logical operations. Now this is a typical common emitter amplifier output characteristics. So what we have learned that this is a class A amplifier because the signal is evenly here amplified at the both sides. At the center of Q point is located at the center. So we have described, if you remember in the earlier classes, we discussed when we are discussing the amplification or amplifier, transistor amplifier, three regions were defined. Region 1 is a cutoff region, here the cutoff region where base current is 0. Region 2 is a saturation region where the base current is maximum, okay, 9.2, let's say it is a maximum current is flowing through. And region B, which is the PC max, where the maximum power is dissipated. These were declared as a prohibited regions at that time for this amplification process. But for digital electronics we don't use this middle region, neither this region. We use these two regions, cutoff region, and you can see that it's a switch suitable for the switching, like a transistor is in an off state and an on state. So here we force this transistor either be in the off state where when we make base current is equal to 0, that is the off state. When we make the base current maximum, that's 100 microampere, so it is in the on state. So this is a simple logic behind how we use this as a on and off state. So we will connecting all these on and off states at the input, whichever you at that particular requirement. Accordingly the gate we make that it is on 1, it is off, it is 0, so on and off. These switching levels are utilized over there. So now we move on. So this is the typical the table, called the truth table, in which we have the OR operation. You can see 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 means both switches A is on, B is on, then Q is on. Okay, the bulb will be on in all these three states if any one of the input is in the state of 1, or all of its inputs are in the state of 1, the output is 1. This is the typical example or the definition of the OR gate operation. Now the next logic gate is the logic AND gate or logic AND function. The logic AND gate or the logic AND function output is only true when all of its inputs are true, otherwise the output is false. Means here if output is true, means output is 1, it has to be that all input has to be 1. Otherwise, in case if any one of its input is not 1, that is 0, and output you are getting the 1, that is the false state or the false condition. So this is now the discrete circuit we call here, made from the switches and a battery and a bulb. Okay, so what we have this time now, these two inputs, these two switches are connected in series. So let's say A is 1, B is 0. This is on, we make it on, turn that switch on, but B is 0. The circuit is broken, the current will not be passing through and the bulb will be in the off state. Means it is 0 So any one of them is 0 or both are 0, output is equal to 0. So if we make A is 0, B is 1, we make it, turn it on, switch is on, but again it is off. Unless until both are on. This is the on state switch, this is also on state, A is 1, B is 1, then the current will pass through this circuit and this bulb will turn on in the state of 1. So that is the stage of the logic AND gate, how it works. So it is just simply a AND gate means A and B, A dot B, multiplying, the operation is performed. Now look at the truth table again. 0 into 0 is 0, 0 into 1 is 0, 0, 0, 1 into 0 is 0, 1 into 1 is 1. This is a typical the AND operation. Means here we must have inputs, the bulb will be turned on if both of the inputs are in the state of on. There is one switch is A, switch A is on, switch B is on, then the bulb will be turned on. Otherwise any of any one of the input is 0, in this case this is 0, this is 0, or both of 0, then output will be equal to 0. Now this is the next logic NOT gate. We haven't yet done this. These are the three basic gates: OR gate, AND gate, and NOT gate. The logic NOT gate function, the output is true when its single input is false, and false when its single output is true. This is called complementary gate or the inverter gate as well. Input is A, the output is A complement, means whatever the input we provide, it brings that to the inverted or the opposite to that. If A is 1, then Q is 0. If A is 0, Q is 1. So complement of 0 or the inverter means 0. We put a bar, we call it this complement. When we put a bar means it is the complement, means it has to be inverted. This number, binary number, has to be inverted from 0 to 1. So that what complement means or inverter means. Whenever put a bar, it means the complement, and complement means you invert that number, the state, whichever state it has, opposite to that one. If it is 0, it is 1. If it is 1, it is 0. So if A is equal to 0, and then A complement is equal to 1. Now the typical representation of this NOT gate is given by this circuitry. We have got now here the switch A. Okay, so we have, this is the bulb. Now bulb is the condition output. This is the output. It will turn on state or off state. So if we make A is equal to suppose it is A 0, what will happen, the current will pass through and the bulb is turned on. So Q is on. So when it is one state. If in the off state A is 0, means current is not here. We have the in parallel it is connected, switch A is connected. So when we turn that on, what will it will short circuit the bulb. So when we turn that on, the current will pass through this will bypass the bulb. The current will be passing through this branch and the bulb will be off state. So A is 1, then Q or the output or the bulb, Q is equal to 0, sorry, Q is equal to 0. When A is 1, Q is equal to 0, that means bulb in the off state. Now this is the smart truth table for that. In the two states we have got now 1 and 0. So if A is 1, then Q is 0. If A is 0, Q is 1. Boolean expression, Boolean will be the logical expression, we get the algebra of logic, we call it the Boolean algebra. We will be doing in the next coming topics. So that we call or describe as a Boolean expression A complement. Now the next gate is the logic NOR gate or logic NOR function. The logic NOR function output is only true when all of its inputs are false. Otherwise the output is always false. So this is the symbolic representation. What we do, we put a NOT gate in terms of in front of the OR gate. This is the equivalent circuit we represent, but this is the typical actual we represent like this: an OR gate with the bubbles here, bubble right at the tip. this will represent a NOR gate. Means the the OR is inverted, means whatever you have got the output of the OR gate, you take that output as an inverted form. So that is the typical NOR gate. So what we have got now, this is the equivalent circuit in the circuitry, electrical circuits, battery, bulb. This is a series resistor to control not to burn out or the short circuit, it is the battery is not overloaded. Here we have A, B2 are connected in parallel. Now if you can see, it is saying that the NOR operation is done, that all of input should be false, means all of its input should be 0, in the state of 0. Now if A is 0, B is 0, the current will pass through and it will be turned on state. It is also known as the non-equality detector, that means the equality detector. In case we will see that both this is the NOR gate, not that will be in case of exclusive or exclusive NOR gate. This is simple gate. What we have when we pass we switch, both of these are in the off state, the current will pass through. But if any one of its input is in the on state, current will not pass through the lamp will be in the state of off position. That is because if A is 1, it will be bypassed, the short circuit here. This one, the lamp is being short circuit, the current will pass through that, so output will be equal to here in that case will be equal to 0. If any one of it is 0, output is 0. So this is a typical the NOR gate. Now this is the truth table for that NOR gate, that is the 0 0 1 1 0 1 0 1 1 0 0. If you remember, in case of OR gate we get 0 1 1 1 3 1s over here. So it's the inversion or inverter of the OR gate. So we invert 0 1 1 to, that is 1 0 0 0. So 3 zeros are there. So that is the typical NOR gate. Next is the logic NAND gate. These are very useful gates. NOR gate and NAND gate, these are also termed as universal gates. We can make, in the coming topic we will show that we can make the any kind of gate from these gates, and that is very useful and helpful. The logic NAND gate output is false when all of its inputs are true, otherwise the output is true. So that is the case where when we put these two switch in parallel, then what we have, this will demonstrate if input here all of its inputs are false, and all of these are 0 0 0. If any one of its 1, then it is true, that is it is equal to 1. But if all of its inputs are false, the inputs are true, otherwise it is the output is only false, output is 0 if all of inputs are true. If all of its inputs are 1 1, then that is output is equal to false. So let's see now, if A is 0 and B is 0, means the current will pass through. So Q is equal to 1. A is 0, that is this is off state, this is off state, then output is equal to 1. But if similarly A is 1, switch on, but B is 0, still it is output is equal to 1. B is 1 but A is 0, means it is off and this is on. Again, still the current will flowing through the lamp, and lamp will turn on, it is equal to 1. So for this circuit to have the Q output to be equal to 0, all of its inputs has to be true, means state of 1. This is on, this is on, A is 1, B is 1, the circuit will be short circuited, current will pass through this branch, and output is equal to 0 in that case. So this is the now equivalent circuit for that AND gate and inverter gate. NOT gate, this NOT gate, this is a NOT gate, symbolically represented a triangle and a bubble at the tip of that triangle, and that is a NOT gate. So whatever we have obtained from the AND gate, we invert that value, will give you the NAND gate. So again 0 0, here we have 0 0 1 1 0 1 0 1. is 1 1 1 0. In case of AND gate, what we get 0, we get the 0 0 0 1 in that case, because AND gate. But inverter NAND gate means the inverter of the AND gate or the NAND gate, we get 1 1 1 0. That is the outcome. So we with this we reach to the this section, end of this section, and we'll meet inshallah in the next section again with a new topic. Till then, goodbye and thank you.